Hello, I'm Harold McNair. In this section we want to talk about the instrumentation, the parts of the gas chromatograph. We've shown you this overview earlier: the carrier gas, injection port, the column, the detector, and the data system. In this short section we would like to give you more details. Carrier gas. The carrier gas must be inert and suitable for the detector. In the case of a thermal conductivity cell, TCD, the most frequently used carrier gas is helium. Occasionally hydrogen is used. For the flame ionization detector, FID, flame ionization detector, either nitrogen or helium are commonly used. Helium is most often used, but with the increasing price of helium in the United States and probably the rest of the world, nitrogen being used more often. Finally, the electron capture, ECD, which is a very special detector with high sensitivity, very dry nitrogen, no traces of oxygen present, must be used just because of the basic operating principle of the electron capture detector. An analytical syringe, which we see the borosilicate glass barrel here, a very sharp pointed needle which is used, and we typically inject 1 to 2 microliters of liquids or solutions of solids. In the case of gases, a larger volume gas-tight syringe, typically 1 milliliter of gases, is also injected. Here we see an on-column injector where we have a packed column here, packed, glass wools to keep the column in place. The carrier gas comes in here, passes up around the septum onto the column. The septum is a high-temperature polymeric material which can be pierced repeated times. The syringe needle here pierces through the septums, displaces 1 microliter of a solution of either solids or liquids into this heated injection port. This heated block will vaporize the sample. The carrier gas will carry the sample onto the column where the separation occurs. This septum must be replaced frequently, typically after about 50 injections. Here's a schematic of a packed column, which we've seen earlier, but in a little bit more detail. The stationary phase is actually a liquid phase, typically 5 or 10% by weight of the total packing material. The other 95 to 90% is a solid support, trade name chromosome. The separation depends on the distribution of the sample molecules in the vapor state between the gas moving phase and the liquid phases. Thus, the stationary phase is actually this liquid phase here coated around the solid support. And the carrier gas here is the moving mobile phase through which the sample partitions. Packed columns are typically lengths of 3, 6, or 12 foot in length. Longer lengths are difficult due to the higher pressures required. The outside diameter are typically 1/4, 1/8 inch, simply for convenience of the gas-tight, high-temperature fittings used. Made of stainless steel or glass, easy to make or use. There are a large variety of liquid phases, over 100, which have been used, but the packed columns are not very efficient. They generate only a modest number of theoretical plates, and plate counts are a measure of efficiency. We have a modest number of about 8,000 maximum plates from a packed column. As we'll see shortly, the capillary columns are much more efficient. This actually is a properly named wall coat open tubular column. Vernacular common name capillary column. Commercially available, there are internal diameters of 100, 250, 320, and 530 micrometers, different diameters. The tubing wall itself is a fused silica, and the red liquid phase here is a typical liquid phase as used in the packed columns as well. This film thickness is a very thin film, ranging in size from 0.2 up to 5 micrometers. Very, very thin film. A typical liquid phase is most often 0.25 micrometers, in thickness. The capillary columns, since they are not packed, they're open tubes, long lengths can be used. Commercially available are lengths from 5 to 100 meters. Just for your information, the literature contains one capillary column more than 1 mile in length. Bit of a silly idea, because the air peak takes over 24 hours. Internal diameters, as mentioned earlier, 100 to 530 microns internal diameter. The fused silica is coated with a high temperature polymer, a polyimide, which makes it temperature stable up to close to 400 degrees centigrade. And the big advantage of capillary columns are very efficient separations over 100,000 theoretical plates, meaning very high resolution and or fast analysis. We have only 3 heated zones inside a gas chromatograph. Schematically here, injection port, the column, and the detector are all heated, but for different reasons. This injection port is heated simply to vaporize the sample so that the carrier gas can carry the vapors onto the column. The column is heated, often in a temperature programmed mode, increasing column temperature to control the retention time. Lower temperature, longer retention time. Higher temperature, shorter retention time. And finally, the detector is heated simply to keep it clean. We do not want to have either the sample coming from the column or the column bleed coming from the column to contaminate the detector. So the detector is always heated slightly hotter than the maximum column temperature, simply to keep it clean. We have 2 modes of operation with respect to column temperature. Isothermal means simply a constant column temperature during the entire analysis. And here's a good example. This is a separation of a kerosene, which has up to 15 carbon atoms and more, performed isothermally at 130 degrees centigrade. Here we see a series of C8 isomers unresolved on this first peak. Here's the C9, C10, C11, C12. But in isothermal conditions, the higher boiling C15 elutes very slowly, between 90 and 95 minutes. Thus, isothermal is not appropriate for this particular sample. Temperature programming is an increase in column temperature with time, almost always a linear increase. Thus, we often start isothermally and then a normal 4 degree per minute increase in column temperature for temperature programming. Let's do the same sample now under temperature program conditions. Remember, the other sample was done isothermally 130 degrees. If we start colder, we not only see the C8 peak, we find contamination from both the C7, C5. Much better resolution at the lower temperature due to this low temperature. As we increase the sample temperature, though, we see a nice separation of the 9, 10, 11, and now the C15 peak, which earlier took over 95 minutes, now elutes somewhere around 22 minutes. But now we also see a C16, 17, 18, 19, peaks which were not possible. They would not have been observed because they would have taken possibly 10, 20 hours, even days to elute, if they eluted at all at the isothermal temperature. The last point to discuss are data systems. Today, most data systems consist of a computer workstation. Typical price might be around $5,000, $7,000, depending a little bit on the software available. They are by far the most flexible, the most powerful, and also the most expensive. Still available, still used widely, are printer plotters, integrators. Easy to use, a more moderate price, and they do give you basically the same quantitative data, but not with the flexibility and the format reporting associated with the computer systems.